David Smith here with another Flipped Classroom math video. A few tips before we get started. Remember, you can always pause the video if you need to catch up with your notes. You can also speed up or slow down the playback if that helps. Finally, you can turn on the captions so you can see my words going by at the bottom of your screen. Today's lesson is on optics, lenses, and telescopes. So let's get started. I've drawn two types of lenses, and we're looking at the cross-section of the lens. So the lens is circular, coming out of and going into the board. This is the cross-section of the lens. We have convex lenses and concave lenses. And a convex lens curves outward like that, and a concave lens curves inward. Now, these lenses do different things to light. So when you have light coming in from a distant object, the light rays are all parallel, and here's what happens. A convex lens will focus the light like that. So it focuses the light to basically a point where it's in focus. This distance that it takes is called the focal length. So that's the length from the middle of the lens to where the light beams converge at a point. That's the focal length there, and there's my lens. Now, a concave lens does the opposite. It disperses light. So the light goes out wider. But it does not focus the light. There is no focal length for this. Okay, so let's put this in here. It focuses light. And this disperses light. Okay, we have two other configurations of convex and concave lenses that you should know about. This is called a single convex. One side is just flat. It's not convex. That's the convex side. And by the same token, we have a single concave where one side is just flat and the other side is concave. All right, let's take a look at how lenses work within a telescope. And this telescope is a certain kind. This is a refracting telescope. And what we've got is we've got two lenses. We've got the objective lens. This is the lens on the outside, on the far away from the eyeball. And we've got the eyepiece lens. This is the one that you put your eye up next to when you look through a telescope. And so what happens is the rays of light come into the telescope. They're parallel. And this is going to focus it all the way down to some focal length like that. And so this would be the focal length of our objective lens. So I'm going to call that FO. And then the light rays are going to pass on through and they're going to come to the eyepiece lens, which also has a focal length, and we'll call that FE. And when you focus a telescope, you are moving these lenses with respect to each other so that you bring these two focal lengths to match up, and then your object is in focus. Okay? So, and then what happens is the light rays come out of here in a parallel way, and then your eyeball also has a lens, and your eyeball focuses that light on the back side of your eye, on your retina, and that creates the image that then gets translated to your brain. So to summarize, parallel beams of light go through the convex objective lens. They get narrowed down to their focal point, and then that focal point is coordinated with the focal point on the eyepiece lens so that they meet at the same place. So these lenses are going to spread back out. They hit the eyepiece lens going this way because these light rays are diverging. They're going to get bent inward to be parallel. They're going to hit the lens on your eye, that's your cornea, that's on the front of your eye, and they go through that lens, they get converged again, and they get focused on the back of your retina, and then you have an optic nerve that goes to brain. And your eyeball sees that image. Now there's a curious thing about this telescope, is here's the bottom and here's the top. The bottom light ray is being translated to the top, and it's going to go through to the eye. So this type of telescope makes the image upside down. Okay? And that's how a refracting telescope works. Okay, now here's a way that a concave lens might be used with a telescope. Notice how my objective lens is convex, just like before, but now my eyepiece lens is concave. So let's write that down. Eyepiece lens concave. And this is concave lenses and telescopes. Okay, so how might this work? Check it out. For this to work, the focal length of the objective lens has to be beyond the eyepiece lens, because here's what happens, is that the light rays will come in. Remember, they all come in parallel on this side before they hit the objective lens. And they're going to go like that. So notice how we don't have a focus. Our focal length is probably about there. Let's draw that on there. FO for objective. And we'll just say that's about there. Now what's going to happen is the convex lens is going to disperse the light. So they're going to go back to being parallel. Okay? And then they're going to hit the eye. Here's the cornea on the eyeball. And they're going to get focused by the cornea, the eyeball's lens. And they're going to go focal point on the back of the retina. And again, it makes an image to the brain. So this is a different way to do that. It doesn't focus it. The second lens is actually within the focal plane of the first. And it takes those converging beams of light and makes them parallel. And then your eyeball further focuses it so you can see it on the back of your retina. Now, there's a difference in the outcome of this type of a telescope versus the one we just looked at, versus the refracting telescope. Pause the video and think about that. What's the main difference that you can see here in terms of the result, in terms of what you see? Okay, if you said the image is not upside down, you're right, because here's the beam from the top of our image. It's going down, and now it's being made parallel again and going down. It never switches like it did in the refracting telescope. So image is right side up. Okay, let's take a look at how telescopes magnify. Because face it, that's what we use them for. There are things that are way far away from Earth that we'd like to take a look at. So we use telescopes to magnify the light so it becomes more clear, it becomes bigger to our eye, so that we can see them and catch some detail and basically do some science. So let's take a look at magnification. There's a basic equation for magnification, and it's pretty simple. Magnification, capital M, is also called power. Have you ever looked through binoculars and you look on them and it says 7 power or 7x? That's what magnification is. It's also called power. And it's just a fraction. It's the focal length of the objective lens divided by the focal length of the eyepiece lens. It's that straightforward. So let's take a look at an example. Here's one with an objective focal length of 2.8 centimeters and an eyepiece focal length of 10 millimeters. Pause the video and see if you can write the correct fraction here and then solve it and find out the magnification. Okay, let's see how you did. Now the first thing I hope that you noticed is that these are not in the same units. So we do need to make sure that they're in the same units. So I'm going to stay in centimeters. So this is 2.8 centimeters. Now 10 millimeters is 1 centimeter. So I'll put that over 1 centimeters. So this equals 2.8 power, or we can write it times 2.8. Oh, I'm sorry. They do 2.8x. That's the standard for that. So the magnification with these lenses is going to be 2.8 times. So almost 3 times bigger. Now that might be nice for looking at something like across the quad or down your street. But if you're looking at like Neptune, 2.8 power is not going to be helpful. So you need like a bigger magnification. And most telescopes, certainly the big ones at the astronomical observatories, have quite big magnifications. Okay, here's an example I want you to try. The objective focal length is 1250 cm, 1250 centimeters, and the eyepiece focal length is 150 millimeters. So go ahead and write your fraction and then do your math and figure out the magnification. Okay, so what I get is I divided my 1250 centimeters by 15 centimeters because I converted my millimeters to centimeters. And then that gives me 83.3 repeating. So I'm just going to round that down because that's not a 5 or bigger. So this telescope would have about an 83 power magnification, which is pretty good. That's quite a bit stronger than the other one that we did. One more type of telescope, and this is way more common in the big league telescopes that look at distant galaxies and all of that kind of stuff. This is called a reflecting telescope. So it does use lenses, but in this particular telescope, we've got 2 mirrors instead of lenses. So let's take a look at how that works. We have this big mirror. It's at the bottom of the telescope. The starlight or whatever moonlight is coming in this way. The light rays are coming in that way. And we've got this parabolic mirror right here. So let's draw some incoming rays. They come in, boom, like that. And maybe another light ray like that. And remember, we're drawing just a couple light rays. In truth, this thing is suffused with light rays. There's light rays everywhere impinging upon this parabolic mirror. Now, here's the thing about a parabolic mirror. As you can tell, this is going to do a little bit of the same kind of focusing that a convex lens does. Since this is a curve, these light rays aren't going to reflect straight back. In fact, what they're going to do is they're going to reflect to this mirror right in here. Check it out. So now we have this mirror. This is a reflecting mirror. It's mounted inside the tube. And what it's going to do is it's going to reflect our light rays down to this eyepiece, which is on the side. So what's going to happen is these guys are going to focus the light, something like that. So that's the focal point. So we have light rays coming in. Let's put arrows on it so you can see. And that is the focal point. Okay? Now, what happens, just like with our regular refracting telescope, is that the beams are going to cross over and they're going to go to the eyepiece lens. They're going to come out of the eyepiece lens all parallel, and then the human eye is going to be right there, and they're going to get focused on the back of the retina. So this is kind of an interesting telescope. You probably would have this pointed up, and the light rays come in, they hit this parabolic mirror, so they reflect and they converge, they get focused, they hit a straight flat mirror. It doesn't do anything to light except reflects it. It's mounted at a 45 degrees, so the light beams just keep on going. They take a 45-degree turn, and then they pass at their focal point, and then they come back to an eyepiece lens, which also has the same focal point right there. So we could have magnification, and we could have an image on the back of a retina. Now, one thing I think you could probably tell is that with this giant reflecting mirror, we're going to be able to get quite a bit of magnification. This focal length is from here to here down to there. So the bigger the objective focal length compared to the eyepiece focal length means we have a bigger magnification. Now you could think, what if we had our mirror wasn't quite so sharply curved and was mounted way back here? Then we could even increase the focal length and get an even bigger magnification for our telescope. Okay, that's it for this lesson. And just to know, we have just scratched the very surface of this topic. There's a lot of math, there's a lot of things to say about lenses, about different types of telescopes. We really only covered 2, and there's obviously more kinds of telescopes, but that gets you started. And maybe you find an interest here that you'll pursue later in your life. Now that you've watched the video, take a moment and write down any questions that you might have so you can bring them to our next class. Remember that you can always watch the video again and perfect your notes. Finally, if you enjoyed the video, please click the like button down below. And if you'd like to help me grow my YouTube channel, please click subscribe.